Here we have a 5 kilogram wagon with no friction on the ground, and resting on it is a 1 kilogram box. The wagon and the box have a static coefficient of 0.5 and a kinetic coefficient of 0.4, and we're asked to find the maximum F where the box won't slip, and for a given F of 4 times gravity, find out how long it will take for the box to slide 20 centimeters off the back of the wagon. So let's look at case A, no slip. And we'll draw a free body diagram of each of the parts. And let's call the wagon B, and we'll call the box A. So for our little box A, we have little mg, we have a normal A, and if you think about it, the force that accelerates the box is friction. It's that coefficient of friction right there that's going to accelerate it. So down here, we're going to have a friction force of mu s times n a. So from there, we can do sum of the forces on A is m a a, and we're going to do this in the I hat direction. And we have mu. Now if you look at this in the y direction, NA equals mg. We have no acceleration vertically, so mu mg will equal MAA. And the m's drop out, and we get the acceleration of A is mu g, and this would be mu sub s, which is 0.5 g max accel. So we can't accelerate this box from below with greater than 0.5 g, or we'll overcome our static friction. Let's draw the free body diagram. This was for A. Draw the free body diagram for B. Force F, let's call it static S. On top of the wagon we have our box M, little m, and they are coupled. It's sticking. So we can treat it as one object, and the frictions become an internal force. It's sort of like a glue that's holding that. Yet we know that we can't accelerate that system with greater than 1/2 of a g, or the box will break loose. This glue will break and it'll slip. So with that, sum of the forces is m plus m a, which will give us F is 5 plus 1 times 1/2 G, or Fs is 6 times 1/2 will be 3G. And if you want to multiply that by 9.8, you can. You'll get 29.4. But there's nothing wrong with leaving it like that for now as well. For case B, F is 4G, so the box will slip. Again, we want to draw the free body diagram of each. And we have little mg. We have the normal on A. And if you think about it, we still only have friction acting on it. Except now it's kinetic. In the y direction, AY is 0, so that the normal on A is little mg. And in the x direction, we get mu Na is m a x, and we have mu mg is m a x. The m's drop out, and once again we get ax is mu k g, or 0.4 G. Notice that that is independent of M and F. The actual value of F below doesn't translate to the small box. Once we exceed that force, once we exceed the 3G, this box accelerates and slides at the same time across the top of the wagon. Let's apply a free body diagram to the wagon. And again, we have a box on here, but it's decoupled. It's sliding. So now they are two systems, and if you think about it, for Newton's third law, this friction force acts to the right, which tells us its reaction would be mu k n a. This is an A up here. So this box feels a friction of mu na to the front, and the wagon feels a rearward mu na. That's Newton's third law. If we add them together, they're going to be 0. It's an action-reaction pair. And again, we can apply Newton's law. sum of the forces on B, MAB, and if this is the positive direction, we have 4G minus mu K and A equals big M only. It's sliding decoupled, so no little m. Now, we get 4G minus mu K little m G for NA, that's big A, equals big M acceleration of B. So the acceleration of B is 4G minus 0.4 and 1 times G, all divided by 5. Which will be 3.65 G. Or if you want to write it, 0.72 G. We have a wagon and a crate. The crate is accelerating acceleration of A. The wagon is accelerating with acceleration of B. And the crate needs to slide back and fall off the back. So we need the acceleration of A with respect to B, which would be the onboard relative. This would be as if this was a pickup truck and you were inside watching this box accelerate away from you. That's what that would be. It would be the acceleration of B, A with respect to B, where B is the wagon. So it's the acceleration of A minus the acceleration of B. Acceleration of A was 0.4 G minus 0.72 G. Acceleration of A with respect to B is negative 0.32 G. Now from here, we can use the distance equation and we'll call that 0. It starts at rest. So we have that term, and there's our time. So the time will be the square root of 2x on A, which is the square root of 2 times negative 0.2 meters. And we're fixing two things here. This is 0.2 meters. And with respect to these occupants, if we're calling this direction positive, that's a negative measurement towards the rear of the truck. And divided by negative 0.32 G, they see the box accelerate away from them going towards the back of the truck. So these are both backwards. There's the negative direction, and that's the direction of its acceleration. And from there we'll get 0.36 seconds and G is 9.8 meters per second squared.